Hello students, and welcome to our lesson on square roots. In the very first lesson we had in this class, we talked about how the perfect squares from 1 to 15 are particularly worth remembering because we often use them in mathematics. And this lesson is going to be the opposite of that, where we are going to use those perfect squares 1 through 15 plus some other ones, but we're going to be going in reverse. So in the past, when we say, or when we square a number, so when we say a number squared, or when we just square a number, we multiply it by itself. So n squared is really just n times n. Or if we do 6 squared, that's 6 times 6, which is 36. Okay, so we've seen that in the past. A square root does the opposite of squaring. It asks the question, what number times itself gives this value? So square root of n times the square root of n will give us n. Okay, so as an example, the square root of 36 is 6 because 6 times itself equals 36. So it does the exact opposite. Now, this symbol that looks like a little down, up, and across, this is called a radical or a square root symbol. And the value inside is called the radicand. Now, the only real reason we need to know that the inside is called the radicand is so we can reference it. So if I want to reference the inside of the square root of 36, I would say the radicand is 36. And that focuses just on what's underneath that radical symbol. So now, as a reminder, this is not the first inverse relationship we've seen. We had additive inverses, where the inverse of addition was just subtraction. We had multiplicative inverses, where the inverse of multiplication was division. And now we have the inverse of squaring is square rooting. And the purpose of all of these is just to undo the other one. So now, I gave you a similar table way back in lesson 1. A perfect square is a number that comes from squaring an integer specifically, where remember integers are the positive and negative whole numbers. So if we square an integer, we get what is known as a perfect square. And I had told you guys to memorize up through 15 squared, which is 225. That, if you actually memorized it, is going to help us a lot right now, which is to go the opposite direction. So you can see that the top of this table has all of the n squared values. So those are all the perfect squares from 0 all the way up to 225. And what we're going to do is write down the square root of each of these. So I have a couple filled in already. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. But we need to fill in the rest of this table. And so by knowing what squared equals the number on top, we can easily go backwards. 0 is kind of a gimme. If you square root 0, you just get 0 because 0 times 0 equals 0. But if we jump over to 16, the square root of 16 is going to be 4 because 4 times 4 gives us 16. Going down the list here, square root of 25 is 5, square root of 36 is 6, square root of 49 is 7, square root of 64 is 8, square root of 81 is 9, square root of 100 is 10, square root of 121 is 11, square root of 144 is 12, square root of 69 is 13, square root of 196 is 14, and the square root of 225 is 15. Now, it's not that square roots or perfect squares don't exist beyond that. It's just that these are the ones that come up enough that it's probably worth committing to memory. For any numbers that are bigger than this, so once we get past 15, then we generally just use a calculator for, and we'll be doing some of that later on. But for the small ones that show up all the time, we should be able to just really quickly jump to an answer. So down here for number 1, we want to state the value of each expression. The square root of 49 for number 1 is just 7. For number 2, the square root of 121 is just 11. And number 3, the square root of 196 is 14. Nice and easy. Now, if we put a negative sign in front of a square root, that is not going to change the operation we're doing. It's just going to tack that negative on at the end. So for number 4, negative square root 25, that negative sign stays in front, and the square root of 25 is just 5. So all in all, we have negative 5. where all we do is take the square root like normal, but then throw the negative in the front. So similarly, negative square root 144 is going to be negative 12, and then negative square root of 169 is negative 13. All right, so now, what if it's not a perfect square? Because let's be honest, most numbers are not. So since most numbers are not perfect squares, their square roots are not integers. And so it's not going to be something that we can necessarily come up with so easily. What we can do, though, is we can estimate these non-perfect squares. Okay, so now we're going to practice estimating. And we have two different ways we can estimate. We can estimate non-perfect roots by stating the two integers that lie on either side of it. So we can say that it's between two integers, or we could be more exact than that, and we can use a calculator to find a decimal approximation of the root. And that will give us a very precise but not technically exact answer. And the reason it's not exact is that we're going to learn more about this in the following lesson, but the square root of a non-perfect square is actually not a rational number. So we're going to introduce what are called irrational numbers in the next lesson. And that's going to show us that an irrational number has to be rounded. So we call it a decimal approximation because it has to be rounded. So we're approximating when we round. But we'll worry about that in the next lesson. Don't stress over it now. So let's look at number 7. We're going to estimate each square root by stating which integers it lies between. Then we're going to confirm our estimate using a calculator where we will round to the nearest hundredth. So we have square root of 8. What we want to do is try to narrow it down to what two numbers are between, or square root of 8 is between. So I'm going to write square root 8 in the middle. And then on each side, I'm going to put a less than symbol. And to the left, I want to say, what is the perfect square that is below 8? So if I think of all the perfect squares that we had in that table, 0, 1, 4, and then we jump all the way to 9. So notice when we go from 4 to 9, 8 is in the middle of that. So the next one smaller than 8 is the square root of 4, and the next one bigger than 8 is the square root of 9. So all I did was use this table up here to reference where is 8? Well, it's between 4 and 9. So that means that the square root is going to be between 2 and 3. So now we get that 2 and the 3 by on each side of what I just wrote. Square root 4 is actually 2, and square root 9 is actually 3. So this shows us that the square root of 8 is sandwiched between 2 and 3. Now we can confirm this with a calculator by just typing in square root of 8. Notice it gives me 2.828, so I'm going to round that to b. The square root of 8 is approximately 2.83 because it says nearest hundredth in the prompt. And 2.83, notice that that is in fact between 2 and 3. And we could have gotten a little more specific with our estimate originally by saying that 8 is closer to 9 than it is to 4. So that means the square root of 8 is going to be closer to 3 than it is to 2. But we really don't have a reason to try to do that because we're either going to say generally what two integers it's between, or we're going to get a very precise decimal approximation, which in this case is 2.83. All right, number 8, we have the square root of 50. 50 is between two perfect squares. Square root 49 is less than it. And then after 49, which is 7 squared, we jump all the way to the square root of 64, which is 8 squared. So we can say that the square root of 50 is bigger than 7, but less than 8. And so now let's just approximate with the calculator. Square root 50 is 7.07 if we round to the nearest hundredth. So we can say that the square root of 50 is approximately 7.07. And notice that that is in fact between 7 and 8. And notice in deeper detail that 50 is closer to 49 than it is to 64. So it shouldn't be surprising that our decimal approximation is closer to 7 than it is to 8. Number 9, we have negative square root 95. So what I want you to do is ignore the negative sign for a second. Okay, so I'm going to point to it with a red arrow so we don't forget to come back to it. But let's pretend it's positive square root 95. The square root of 95 would be bigger than the square root of 81, but less than the square root of 100. So it would be between 9 and 10. Okay, but now we need to take into account that negative sign. So negative square root 95 is going to be between -9 and -10. But we want to make sure that we write those in the order that it actually makes sense. So when we flip the inequality, we have two options. We can either change our less than signs to greater than signs when we add the negatives, or we can change the order. So I can leave it in the order it is, but add negative signs to it. -9, negative square root -95, and -10. But if I do that, then I need to change the direction of the symbols to be greater thans, where -9 is greater than negative square root 95, which is greater than -10. Alternatively, we could turn the whole thing around. We could leave the symbols in the original direction, but change the direction of the numbers. So we could say -10 is less than negative square root 95, which is less than -9. And the way we know that this is the correct thing is ignore what's in the middle for a second. If we ignore one of the symbols and the square root -95 in the middle, this now just says -10 is less than -9. And that is true. -10 is less than -9 because it's more negative. So whenever you're not sure if your inequality makes sense, you just cover up part of it. And as long as it makes sense with part of it removed, it should still make sense with everything there. All right, so now we're expecting a decimal approximation between -10 and -9. So let's go ahead and find out. We have negative square root 95 is -9.75. So approximately, negative square root 95 is approximately -9.75. And notice that -9.75 is between -10 and -9. So just be careful whenever we deal with negatives. You got to make sure that the larger negative number is actually on the left because it's more negative. All right, so now we're going to talk about comparing roots. We just saw how to estimate them, but that now means that we're able to compare different numbers. So estimating square roots will allow them to be compared with other forms of numbers. We've seen various forms in this class, so we know how to work with them all already. To compare roots to other roots, so if we have a square root and another square root, all we have to actually do is compare their radicands. And remember, we introduced this word at the beginning. The radicand is what's inside of the radical. We only have one of these, so real quick, let's look at number 10. It says state which value is greater. Negative square root 4, oh, sorry, no negative. Number 10 says state which value is greater, square root 43 or square root 55. All we have to do is compare 43 to 55. 55 is bigger, so square root of 55 is going to be greater than square root of 43. All we have to do there is compare the radicands. That's the easiest case. But we can also compare to other numbers. So the next bullet point says to compare roots to whole numbers or decimals, estimate the root to one additional decimal place beyond the given number. And the reason we have to go one extra decimal place beyond is that way when we round, we don't accidentally round in a way that changes the result. So if the numbers are really, really close to each other, then us rounding our decimal approximation might actually change the answer. But if you go one extra decimal place beyond what you need, then it's clear that when you round, nothing will be affected. All right, and then to compare roots to fractions, we're basically going to do the same thing as the previous bullet point, but first we have to convert the fraction to a decimal. That way we can compare a decimal approximation of a root to the decimal form of a fraction. So comparing things that are in the same form tends to be a lot easier. All right, so let's look at number 11. We have square root 18 or 4, and we want to say which one is bigger. Without even turning square root of 18 into a decimal, we already should know that square root of 18 is bigger. Well, how come? We know that the square root of 18 is greater than the square root of 16 because 18 is bigger than 16, and the square root of 16 equals 4. So that tells me that the square root of 18 is bigger than 4. So square root 18 is greater than 4. If we wanted to guarantee that we got that correct, which we really already have, but if you want to see it as a decimal, you can just go ahead to your calculator. Square root of 18 is 4.24, and 4.24 is bigger than 4. Number 12, we want to compare the square root of 75 to 8.5. So what we're going to do is approximate square root 75 is approximately, and because 8.5 has one decimal place, I'm going to approximate the square root of 75 to 2 decimal places. So square root 75 is approximately 8.66, where I need to make sure I bring that second 6 in there to make sure I have enough decimal places to actually compare. So now when we compare 8.5 to 8.66, it should be easy to see that the 6 in the tenths place is bigger than the 5 in the tenths place. So 8.66 is bigger than 8.5, which means the square root of 75 is greater than 8.5. Okay, that decimal approximation makes it nice and clear. Number 13, we have square root of 5 or 23 over 4. First thing we're going to do is turn 23 over 4 into a decimal. When we divide, we're going to get 5.75. And the reason I was able to do that one so quick without the calculator is if you turn this into a mixed number, this is 5 and 3/4. And 3/4 is a very common approximation we use. Okay, 3/4 is that 0.75. So we could have used a calculator, but that one's actually not too bad to just convert by hand. So now we want to compare the square root of 5 to that. So I already know that the square root of 5 is between 2 and 3 because I know the square root of 5 is between square root 4 and square root 9. So it's definitely going to be smaller than 23 over 4. But just to be safe, let's go ahead and say that the square root of 5 is approximately, and we're going to go ahead and just do square root of 5 here, is 2.236. So approximately 2.236. Notice I went one decimal place farther just in case that was going to matter, but in this case it doesn't. 5.75 is clearly larger, so we can say that 23 over 4 is greater than the square root of 5. And again, that one, I didn't need the decimal approximations really, because by doing the approximation just by checking which integers it lies between, I knew the square root of 5 was between 2 and 3, and I know 23 over 4 is bigger than 5, so clearly something bigger than 5 is going to be larger than something that's between 2 and 3. All right, now square root property for solving equations. The square root property is used to solve equations of the form x squared equals a. So we have a variable squared equals a number on the other side. So that a will just be a number for us. So now to solve these equations, we take the square root of both sides. But you may not have been taught this properly in the past, as I've seen with a lot of students. So here's how this works. Because x squared, and in parentheses negative x, the whole thing squared, both give us the same result. So for example, 3 squared gives us 9, and negative 3 squared also gives us 9. Okay, so because these give us the same result, we have to account for the fact that the variable might be positive or negative when we square root both sides. So formally what's happening here is that the square root of x squared equals the absolute value of x, not just x. So what most people have been taught is that if x squared equals a, then x equals plus or minus the square root of a. This is valid, okay? But most people have not been taught the step in the middle that x squared, when we square root both sides here, the square root of x squared on the left is the absolute value of x. And on the right side, square root of a is just square root of a. Nothing changes there. But it's the fact that the square root of x squared gives us absolute value of x that then tells us to put a plus or minus here. Because if the absolute value of x equals a number, that means that x could either be positive or negative of that number. Okay, so for instance, if we had that the absolute value of x is equal to 9, that would mean that x could equal 9 or x could equal negative 9. Because both of those, when we do the absolute value, give us positive 9. So now, luckily, we don't have to write this absolute value step every time. It's just important to know what's going on behind the scenes. So we can do what's over here on the left, which is that when we square root both sides, we just have to remember to put a plus or minus in front of the square root on the right side. And that's what we're going to actually do moving forward. But I wanted to make sure we're all clear on why that happens. the square root of x squared gives us the absolute value of x, which means that the answer could be plus or minus whatever the square root of a is. All right, now let's do the examples. It says solve each equation, round to the nearest tenth if necessary. So for all of these, we're just going to be square rooting both sides. X squared equals 25. If we square root both sides, we get x equals plus or minus the square root of 25, where I'm just applying the rule that I circled in pink up above. If we do x squared equals a, square root both sides, we get x equals plus or minus the square root of a. So now we simplify it to x equals plus or minus 5 because the square root of 25 is 5. For number 15, y squared equals 121. Same first step, square root both sides to get y equals plus or minus the square root of 121. And then when we take that square root, we get plus or minus 11 for y. Okay, so no, those are the nice cases where we have perfect squares. But number 16, when we square root both sides of z squared equals 7, we get z equals plus or minus the square root of 7, and that is not a perfect square. So in most cases in math classes, you would actually stop there, and plus or minus the square root of 7 would be the best answer. But because this question specifically says to round to the nearest tenth, we are going to go ahead and get a decimal approximation for square root 7, which is 2.6457. Keep going. And we're going to round that to the nearest tenth. So it's going to be 2.6 because the number next to a 6 is a 4. So I'll keep it at 2.6. And my answer will be z equals plus or minus 2.6. And because I just approximated, I'm actually going to change my equals to approximately, this wavy equal sign. Z is approximately positive or negative 2.6. Okay, so now why do we care about this? You're probably thinking, I don't do square roots in real life. Well, you could be doing square roots in your real life. So let's take a look at our applications. If we have a square park that has an area of 784 meters squared, and we want to find the length of one side, we can do so by setting up an equation and then using the square root property. So first things first, it says a square park, so I'm going to draw a square. There we go. We got a square. The area inside is going to be 784 square meters. And what we want to do is find the length of a side. So because it's a square, both sides are the same length, so we'll call them x. So now we have that the area of this square equals 784, but we should know that the area of a square is just length times width, which in this case, because they're both x, that gives us x times x, which is x squared. So the equation that models this scenario is that x squared equals 784. Now applying the square root property, we get x equals plus or minus the square root of 784, which real quick on our calculator, square root 784 is 28. So we get x equals plus or minus 28. In the previous problems with no context, we would be done. However, this is an application, so we have to interpret this result. We are finding the length of a side. A length cannot be negative. All right, so even though we get two answers, plus or minus 28, we have to throw away the negative one because the only thing that makes logical sense for a length is to be positive. So we would say that the side lengths are 28 meters, where I do not include that negative answer in my result because it is impossible to have a negative length. Okay, one more, number 18. A TV screen measures 50 inches diagonally. If the screen height is 24 inches, estimate the width using the Pythagorean theorem. So first things first, let's draw a TV. Okay, there's a rectangle for our TV. And we're told that the diagonal, so from the bottom corner to the top right, is 50 inches. We're also told the height of this TV is 24 inches, so I can put that over on the side. And we're trying to find the width, so I will write W down here at the bottom for width. So now it tells us to use the Pythagorean theorem to solve. The Pythagorean theorem is a squared plus b squared equals c squared. And this is how you can find the hypotenuse of a right triangle. So notice in my diagram, I have a rectangle, so all the corners are right angles. And when I divide the rectangle in half diagonally, I have a right triangle in that bottom section. So when I use the Pythagorean theorem, a squared plus b squared equals c squared, my two side lengths, w and 24, are the a and b, and then the hypotenuse is the 50, which is c. So when I plug into my formula, I'm going to have that a squared is actually w squared, b squared is going to be 24 squared, and c squared is going to be my hypotenuse squared, which is 50 squared. So now this one's a little bit harder to solve because we can't just square root right away. The first thing I'm going to do is square all these numbers. So with my calculator real quick, 24 squared is 24 times 24. That's 576. And I also need 50 squared, which is 2,500. So I'm going to take into my problem those two numbers. So we now have that w squared plus 576 equals 2,500. And now it's a 2 or 3 step equation, depending on how you look at it. If it was just w, then all we would do is subtract 576 from both sides and be done. But because it's w squared, we are going to have to also square root it. So first, I use the additive inverse to move this 576 to the other side. That leaves me with w squared equals, and when I do that subtraction, 2,500 minus 576 is 1924. And then now I'm going to square root both sides to get that w equals plus or minus the square root of 1924. And that's not a perfect square and not an easy number to work with. So square root 19 or 1,924 gives me approximately 43.86. This problem does not tell me what to round to. It just says estimate. So we could say that it's about 44 inches would be a reasonable estimate, or I'm going to go to 1/10. So we're going to call this 43.9 inches. So we're going to go ahead and claim here that the width of the TV is about, and what was it again? 43.9 inches. Okay, so now just to be clear, we had plus or minus in our result for W, but just like the previous problem, we're finding a width, which is a length, so we have to throw away the negative result and we only keep the positive value. And then I rounded to 1/10 because it didn't specify, it just said estimate. So likely we would say just 44 inches in real life. If you asked me this question in person, or if you looked at a TV box, it would probably say the TV is 44 inches wide, but I kept it with an extra tenth on there to be a little bit more precise. So 43.9 inches. That's all I got for you guys in this one. Hopefully you enjoyed learning about some square roots, and I will see you in the next one.